So this video is all about ozonolysis, and I'm just going to put it in one big video with one chunk describing the whole thing. But I've already described a couple of different pieces that are relevant to this in a couple of different locations. Namely, this is a syn additions idea, so we've talked about that. I've done some of the workup ideas in that same video. And fundamentally, the reason why this video exists is because going through the magic was inspired by this video. This is the video where I walk through the most interesting of all the weird rearrangement sort of things. And once again, I'm not doing it because I expect you to know this in the end. I'm doing it because it illustrates some really crucial ideas that will come back, one later in this course and one that's sort of the foundational idea behind Chem 241, behind Organic 2. So the core idea that you need to have in order to understand the entire mechanism is going to be that oxygen-oxygen bonds are super weak. And in fact, that's true for any electronegative atom bound to another electronegative atom. A bromine-bromine bond, a chlorine-chlorine bond, those are, again, unusually weak. And this comes in handy later in Organic 1 when you hit those bonds with light, causing them to fracture into radicals. So when we get to radical chemistry, you're going to take advantage of that. Again, these are bonds that exist between two electronegative atoms, neither of which wants to share. And so the most likely outcome is that they just sort of split in half. So anyway, if you could provide an extra source of electrons, then it turns out that having a group of oxygen-oxygen bonds like you see here is bad, and this will want to rearrange into any other kinds of situations that are going to be better outcomes. So we're going to try to walk through that. And then, if you go on to Organic 2, the key feature of a lot of the chemistry that dominates Organic 2 is this thought right here, which is that a carbon-oxygen double bond is really strong. And by really strong, I mean it's worth more than two carbon-oxygen single bonds. If you have a pair of carbon-oxygen single bonds, then you're going to want to convert them into a single carbon-oxygen double bond if you can. Again, this is a much better place to be than this is, and that's going to drive a lot of the rearrangements that we see here. As far as what I want you to know from ozonolysis, I want you to know that essentially when you bring ozone into a double bond, what you will do is clip that double bond with your molecular scissors. A whole bunch of black box magic happens. Nothing that shows up in here is something that I want you to know. But then there are three different main workups available to you. There's the mildly reducing workup there, there's the oxidizing workup there, and then there's the fully reducing workup there. So this is mild reduction, then we have oxidizing, then we have full reduction. And in some ways, the normal workup here is to lead to ketone and aldehyde, where once I've numbered the original starting material this way, 1, 2, 3, 4, 5, 6, 7, then you see that you're going to end up with an aldehyde at carbon 7 and a ketone at carbon 2, whereas if you do an oxidizing workup, you would end up with a ketone at carbon 2 and a carboxylic acid at carbon 7. And if you're doing the full reduction, then you end up with alcohols at both places, but specifically the alcohol at location 2 is going to be both enantiomers, so you're going to have the racemic. And again, if there's a core thing that I want you to know from this, it's the predictive products idea that you clip and replace with oxygens, and then depending on which workup you choose, you either have double bonds or alternatively single bonds, and again, you get to manipulate that. But now let's talk about what's actually going to be happening there, and as always, what I want you to do is to draw out a good Lewis structure for any reagent that you're planning on using in a mechanism. And once again, what we have here is ozone, which has the relatively bizarre looking Lewis structure drawn, and of course there's resonance for it, but the key feature is that the oxygen in the middle has a plus charge on it, and one of the oxygens on the end will be drawn as minus in one of the resonance contributors, and in the resonance hybrid, both of these oxygens have half a minus on them, whereas the oxygen in the middle has a plus. But mechanistically, what's going on here is actually taking advantage of the weak oxygen-oxygen bond idea here. But it also is fundamentally about the fact that this oxygen has a plus on it. And when an oxygen has a plus on it, almost always what that means is that you have three bonds in a lone pair. And the only way to solve the problem of the oxygen being plus is to take a nearby bond and turn it into a lone pair. Rather than attacking the plus itself, what you do is you take the double bond and you turn it into a lone pair. And that's only going to happen if you have a source of electrons for this oxygen right there. So this pair of electrons from the double bond comes and causes that to kick onto there, which solves two of the problems simultaneously. However, there's an oxygen that has too much electron density as drawn, and there's going to be a carbon with a plus on it, unless, of course, you draw the key final arrow. So you end up making this particular set of arrows happen, which leads to this ozonide intermediate. At the moment, it's relatively stable. Everything has a neutral charge to it, no formal charge, but again, we have exceptionally weak bonds here. here. So what's going to happen is we're going to do some odd rearrangements here, and really what we're trying to do is solve both of these problems simultaneously. We have very weak oxygen-oxygen bonds, and we'd like to be able to create carbon-oxygen double bonds if we can, and both of those thoughts are going to be the driving force here. Let's say we were going to break this particular bond, this oxygen-oxygen bond, and we were going to create a lone pair, and that would be an O- right there. That wouldn't happen unless we have a source of electrons that made this oxygen happy. But lo and behold, what if we fragment this carbon-carbon single bond as drawn and give it to make a carbon-oxygen double bond? So again, it's this source of electrons that allows that bond to break. What we're doing is creating a strong bond, and we're getting rid of a weak bond simultaneously. So this is good on balance, although it will leave a plus behind at this carbon, but lo and behold, this oxygen has the ability to donate some of its electron density down as follows. Let's draw what that looks like in the immediate short term. Now, just right at the moment, I've drawn it this way, so I haven't changed the shape at all. All I've done is create a double bond there, and I've created a double bond there, and so this dotted line doesn't exist anymore, but I just had it there so you could see how the two structures were related to each other. So of course, the dotted line does not exist. We have broken the carbon-carbon bond that existed briefly in this ozonide intermediate, and now we have created this guy right here. And this carbon-oxygen double bond is fine, and this carbon-oxygen double bond is less fine because we have a plus on this oxygen, and we have a minus on that oxygen. And at the moment, we are not particularly happy. But what if we could simply rotate around this bond and go ahead and point that other oxygen down a little bit? So all I've done is rotate this carbon-oxygen double bond down a little bit, so now it's pointed down away like so, and everything else has stayed exactly the same. And of course, this is not even an equilibrium step, it's just simply a rotation. So it's the same molecule, but all I've done is rotate the one down. But now what you see is that this O- is kind of pointed the right way to donate some electron density into this carbon-oxygen double bond. And though that might not seem like a good thing, it does allow us to solve one particular problem, and that is the problem of having an O-. But if you're going to do that, that would then allow this particular double bond to slide over and make a oxygen-carbon single bond. So what we're going to do is pop that over, and the reason why that happens is, of course, it allows us to solve the true problem here, which is the fact that that oxygen has a plus on it. And where we end up as a result of having done that sequence of arrows is now this molozonide intermediate. And what we have now is a different arrangement than we did back there, but what we've successfully done is break at least one of the oxygen-oxygen single bonds and create something that's a bit better energetically than what we have. So this is, in fact, the intermediate that's going to be stable enough for us to isolate if we want it. Now, I wouldn't recommend you actually try to isolate this material. It turns out that having peroxides is really still unstable. I had a friend of mine in graduate school who was working with a little bit of a peroxide. She didn't realize she had it. She put it into her rotary evaporator and evaporated off all the solvent down to dryness, and when she went to remove that from the rotary evaporator, the rotovap blew up, and she ended up covered in glass, and in fact she had a chunk of glass sticking out of her safety glasses, and so it was remarkably important that she was wearing those glasses, otherwise she might have lost an eye, and this is one of the reasons why we care a great deal about safety glasses. So in any event, don't try to isolate this. However, it can be isolated, and people have gotten NMR of these species, so we know that this is something that actually exists. So in any event, what happens here is you end up clipping this by means of a weird series of rearrangements. First, the ozone's attacked, which creates this ozonide intermediate. You do some weird, bizarre rearrangements that basically amount to trying to get rid of oxygen-oxygen single bonds in order to create, at least briefly, carbon-oxygen double bonds. And then we rearrange again, and we end up here. And so what's actually in the black box is material that looks like that. And all I've done here is just redraw it, sort of looking down on it, so that you can see how this is comparing to the final products that you end up isolating. Again, you end up attacking the double bond, you make this weird 3 oxygens in a row intermediate, it rearranges, you make this weird 2 oxygens and 1 oxygen sort of thing, this kind of weird bicyclic thing, then gets reduced in the presence of zinc, again taking advantage of the fact that a carbon-oxygen double bond is really good. So what the zinc is really doing is breaking that bond right there, the peroxide bond, which is again super weak. So you add in either some zinc or some dimethyl sulfide, either one, that's the source of electrons you need to cause that to break, and then this will fragment down into ketone and aldehyde. If you add peroxide instead, well, you're breaking that weak oxygen-oxygen bond as a way of inserting a new oxygen into carbon-7. If instead you add borohydride, you're adding H- to all these things, and you end end up making the diol instead. At the core, ozonolysis, what it does is clip double bonds and replace them with a series of oxygenated intermediates. You get to decide which ones you want by means of the workup. As far as the mechanism, I don't care that you know any of this. I just wanted you to see it at least once because it illustrates some of the key rules that are going to matter. And the rule that matters the most for this course is the fact that oxygen-oxygen bonds and bromine-bromine bonds and chlorine-chlorine bonds are exceptionally weak. So if you see them, you should think, oh, that really wants to break and become anything else. And then if there's going to be another rule you keep in mind, especially when we talk about tautomerization, it's that carbon-oxygen double bonds are strong relative to two carbon-oxygen single bonds. This is the magic. This is what was behind the black box. But as far as what you actually need to know, treat this compound with ozone, choose your workup. These are the materials you end up making.